All right, before we do another example, I want to just illustrate to you differentiating powers of y versus powers of x. So when you differentiate d dx of x cubed, right, we normally think about this as just 3x squared, and that is what the answer is. But if you want to sort of help implicit differentiation to make sense, you can think about it as 3x squared times the derivative of x, but the derivative of x with respect to x is just 1, and so you get out 3x squared, versus if I want to take the derivative of y cubed, I would say, well, that's just 3y squared times d dx of y. Well, d dx of y is exactly dy dx, so I get out a 3y squared dy dx. And so the point is, whenever you actually differentiate a power of y, you kick out a y prime from the chain rule. And you can think about exactly the same thing happening with x. It's just that the derivative of x with respect to x is 1, and so you never see this part. So it's actually the same chain rule in both cases, but one of them sort of disappears. Okay, so I want to do a really fun example with you. Really, it really is fun. Here's this equation, and I'm not going to graph it first. We'll graph it later, but I want to go ahead and find the general formula for dy dx, and I want to find the equation of the tangent line at this point. Probably after we do a and b, we'll look at the graph, and then we'll still figure out c without thinking about the graph too much. So let's dive in part A and see if we can work this out. So on the left side, nothing too crazy happens. You just take the derivative of x cubed. Let me slide this up here. Take the derivative of x cubed, which you know is 3x squared, plus the derivative of y cubed. We just did this. You know you're going to get a 3y squared dy dx equals. It's the right side where things begin to get a little more crazy. And so what I want you to realize is that since I'm thinking about y as a function of x, I actually have to use the product rule right here. I have x times a function of x, and so I've got to use the product rule. So I'm going to group these as 6x times y. The derivative of 6x is just 6 times y, which is y, plus 6x times the derivative of y, which is dy dx. That's how you actually do it. And now you have to algebraically solve for dy dx just like before. So I'm going to group all the terms that have a dy dx in them together, and then I'm going to move all the terms that don't have a dy dx over on the other side. And so I'm going to end up with something like this. I'm going to have 3x squared minus 6y equals 6x dy dx minus 3y squared dy dx. Now I'm going to factor the dy dx out of this side, and so I get a 3x squared minus 6y equals 6x minus 3y squared times dy dx. And now I'm going to divide both sides by whatever's in front of dy dx, and so I get a 3x squared minus 6y divided by 6x minus 3y squared equals dy dx. And so the point is I'm going to cancel a 3, and I can say dy dx is what? X squared minus 2y over 2x minus y squared. And I'll just point out to you that if you multiply top and bottom by a negative, you might have minus x squared plus 2y minus 2x plus y squared. Same thing, right? You might have this slightly different than the person beside you, depending on how your negatives fall. So it doesn't really matter. Just be aware that your answers might look different. So here's my generic formula for the slope of the tangent line at a point. Now, for this formula to make sense, you have to plug in a point that actually lies on this equation. You can't just plug in random points. Like, for example, x equals 1, y equals 1 does not live on this equation. So it would not give you anything meaningful here, even though you can plug it in. So we are interested in part B, the equation of the tangent line at the point 3, 3. Let's check in our heads. If I plug in x equals 3, y equals 3, I get 9, and 9 is, sorry, not 9 and 9, I get 27 and 27. is 54, and then here I get a 9 times 6 is 54. So I'm good to go. This thing works. So part B says, take your formula that you found in part A and plug in 3, 3. So that we usually write that dy dx, we put an evaluation bar, and you can say the point 3, 3. And that's saying x is 3, y is 3. And so you get what? 9 minus 6 over 6 minus 9. And I'm coming up with just 3 over negative 3 is negative 1. So that's the slope. So now I think about my formula. I've got the point 3, 3. I've got the slope negative 1. So it's y minus the y coordinate 3 equals negative 1 times x minus the x coordinate. I'm actually going to put this down here. And so we can clean this up, and we're going to get y equals negative x, let's see, plus 3, plus another 3, so plus 6. So the claim is this is the equation of the tangent line to this curve at the point 3, 3. Well, let's switch to Mathematica and see what this thing actually looks like. So I've got Wolfram Cloud here, and I can run the first one with you. And there is a graph of our curve. I went ahead and threw the axes on there just so you could see where the origin was. I'm actually going to take them off now. Somehow it's a little cleaner. Oops, I didn't mean to take that off. There we go. So the axes are gone, and you get this beautiful spiral, really a nice loop. And so that's the curve. This thing definitely is not a function. You can see that. And so now we're interested in graphing this thing with its tangent line at 3, 3. So let's run the second one here. I've got it all typed in, and there it is. You can see the tangent line up there at y equals 3, x equals 3, and it is indeed tangent to the curve. So that's it. Okay, so let's go back to the notes now. So Mathematica, the question is asking me for at what points on the curve in quadrant 1 is the tangent line actually horizontal? And so I want to solve part C without thinking about what the graph looks like. You've seen it now, but we don't need to have seen the graph to be able to work out part C. So here we go. Let's do it together. So for part C, what I'm looking for, the tangent line horizontal, that happens if and only if the derivative dy dx is 0, right? The slope of the tangent line needs to be 0. Wow, that was a really messy tangent line. Okay, so I'm looking for where dy dx is 0, so I'm going to just copy my formula for dy dx, and I'm going to put it right here, and I'm going to ask myself, okay, where is this formula equal to 0? Well, this guy equals 0. I'm going to erase this part. That is dy dx, and it equals 0 if and only if the top is 0. So x squared minus 2y is 0. So that means that what? Y is x squared over 2. Okay, that's great. But what do? Well, you can plug this back into the original equation. So let's write that down. Plug back into original. And you should ask yourself why. Why can I just do that? And the answer is that anytime you're talking about a slope of a tangent line, the point that you're talking about has to actually be on the curve, which means anytime that you have a point of interest with the tangent line, it has to satisfy the original equation as well. Your point x, y has to lie on the original curve. Otherwise, you can't talk about the tangent line. So we're talking about the equation for the tangent line. We're solving, we get this equation, and whatever point satisfies this equation has to satisfy the original curve as well. So we're going to go back up, grab the original curve, we'll copy it, let's drag it down. Whoops, here's the original, and I'm here, and now I can plug in y equals x squared over 2, and so I end up with this x cubed plus, let's see, x squared over 2 cubed equals 6x times x squared over 2. Okay, and I'm going to need another page here, so let's just, let's see, whoops, where are we? No, yeah, I'm sorry, I'm going to have to slide this down. That's fine though, okay. We're right here. All right, so at this point, I've got to do some very exciting algebra, so I get x cubed plus x to the 6 over 8 equals 3x cubed. So I'm going to move this over, and so I get what? X to the 6 over 8 is a 2x cubed, and so I get x to the 6 equals 16x cubed, right? And so now I'm going to, typically speaking, you want to subtract and factor. So I'm going to think about this as x to the 6 minus 16x cubed equals 0. And so then I'm going to have an x cubed times x cubed minus 16 is 0. And so I get either x is 0, this equals 0 means x is 0, or this guy equals 0, which means x cubed equals 16. Think about what that means, right? 16 is 2 to the 4th, so x is the cubed root of 2 to the 4th, or if you want, that's just 2 to the 4/3. We're going to get some messy answers here, it's no problem. Well, if x is 0, then y is 0, right? Going back, y is x squared over 2. If x is 2 to the 4/3, then y equals 2 to the 4/3, oh my, squared over 2. Yes, this is awesome. So we're going to get, let's see here, we're going to get, you multiply, and we're going to get that this is 2 to the 8/3, right? 4/3 times 2 over 2. And then when I subtract, right, I can think about 2 as 2 to the 3/3, subtract, and you're going to end up with 2 to the 5/3. So our two solutions here, so we get 0, 0, and the point 2 to the 4/3, comma 2 to the 5/3. Those are the two places in the first quadrant where the tangent line is horizontal. And you should ask, is 0, 0 really in the first quadrant? It's the origin. It depends on if we mean the first quadrant including the boundaries or not, right? We went ahead and just captured both of them. And so these are messy points. You can plug them into your calculator if you want. Let's actually go back and look at the picture and think with me. I can't draw with you, but you can see the horizontal tangent at the origin. There's also an undefined tangent at the origin. There's actually two tangent lines at the origin, but you can see that horizontal. And then if you look at the loop, just to, I can't point, it's quite set. I'm pointing right now perfectly at the spot, but you can't see it. Here, let's actually see, maybe we can copy this picture. No, we can't. All right, but if you look just to the left of the point on the curve where our tangent line is graphed, you can see that's where the horizontal tangent line is, and there's only one. So we were able to find that exactly. I want to walk you through again how we did it. We just set the derivative equal to 0, and we got an equation. We plugged that equation back into the original, and we boiled it down, and we solved for x. And we were able to get x equals 0 or x equals 2/4. Both of those you plug into your equation y equals x squared over 2, and you've solved for y. So there's a lot of plugging, a lot of solving, but it's always the derivative, get an equation, back into the original, and then whatever you get for x, back into the equation that you got. It's kind of circular, right? So derivative, and then back again in some sense. So that's how you do it. So we'll end this video here, and then we're going to do one more example in the next video.